Good afternoon, everyone. Let us start today's discussion. So, first of all, we had two questions remaining from the previous week assignment on voltage stability and voltage regulation. So, first, we will discuss those two questions and then we'll move to this week's discussion on uh, your capacitor, use of capacitors in distribution system. So, if you remember last week's this question, so here radial distribution system is given and your value of the line parameters, that is r plus jx of each line, it is given. So this is, let's say, line 1. This is r2 plus jx2. Similarly, for the third line, the line parameters are given in this question. Then the next information that is given is the current drawn by the load at each node. So here you can see 30 amperes at 0.8 power factor lagging. Here it is 20 amperes at 0.9 power factor lagging, and at the bus number 4 we have 50 ampere at 0.8 power factor lagging. So and for this we need to calculate the total voltage drop from this feeder input node bus 1 to the tail end. So normally we say from the head of the distribution to the tail, the total voltage drop. So if you remember the expression for voltage drop, and here we are using the approximate analysis method. So we had derived, if you remember this formula here. So you can see for the drop from OA to OC, so we calculate first the drop from O to A. So for O to A, it is the current drawn here IA times the parameter line here R1. For drop from A to B, it will be IB times the sum of resistance R1, R2. And for IC similarly, for BC, it will be IC multiplied with R1 plus R2 plus R3. So let us calculate that in this question here. So here first let me calculate the voltage drop from 1 to 2. So that will be your current drawn here at node 2, that is 30 amperes. So that will be I2 multiplied with the resistance of this first branch, that is 0.5. So it is just like I r cos phi plus x sin phi, right? So here r is 0.05 times cos phi is 0.85. So multiplied with 0.85 plus x is 0.01. So if cos phi at node 2 is 0.85, what will be sine here? You can calculate it here. So that will be sine of cos inverse of 0.85. So that will give you something around 0.527. So in place of sine phi, you can put here 0.527. And for I2, you can write in place of I2 30. So here you can get it as 1.4331 volt. Similarly, let us calculate the voltage drop from 2 to 3. So for 2 to 3, it will be something like this I3 times node 3, right? So I3 times First, you will add the resistance R1 plus R2. So this is I is for node and this index is for branch for the resistance times cos phi 3 plus x1 plus x2 times sin phi 3. So that I3 here is 20 ampere and cos phi 3 is 0.9. So 20 and cos phi 3 is 0.9. So sin phi 3 you can calculate similarly. That will be sine of cos inverse of 0.9. So that you will get around 0.4359 times R1 plus R2. So 0.05, 0.08, 0.05 plus 0.08 times cos phi 3 is 0.9 plus x1 plus x2. So that is 0.01 and 0.05 times sin phi 3 is 0.4359. So if you solve this, it will give you something around 2.8631 volt. Similarly, for the last branch between 3 and 4, the voltage drop from 3 to 4. So that will be I4 times R1 plus R2 plus R3 cos phi 4 plus x1 plus x2 plus x3 sin phi 4. So let us see the values. So it is 50 ampere at 0.8 power factor lag. So 50 amperes and cos phi 3 is 0.85. Yeah, 0.8. So sin phi 3 will be 0.6 here. 4. So 50 times R1 is 0.5 plus 0.8 plus this is 0.1 and 0.02. 0.1, 0.8 plus 0.02 and this is 0.6. So if you solve this, you will get the voltage drop as 11.6 volt. So total voltage drop you can calculate as sum of all this, right? Total voltage drop equal to, you can say V drop from 1 to 2 plus V drop 2 to 3 plus V drop 3 to 4. So if you add all this, you will get it around 15.8962, which is nearly equal to 16 volts. So answer is option C. Then the last question. So here I think it is same as the previous one. Yes, but here you need to use the exact method for calculation. So similarly here it is, yeah, so already I2 is given to you, that is 30 ampere and at an angle of lagging, so minus of cos inverse of 0.85 ampere. Similarly I3 will be 20 minus of cos inverse of 0.9 and I4 will be 50 minus cos inverse of 0.8. So from this, then I can calculate the branch currents. So similar to the backward forward sweep, if you remember. So I34, this current I34 will be same as I4. And what about I23? That will be I3 plus I4. And finally I12 will be I2 plus I3 plus I4. So this value you can calculate using these values here. After calculating the branch current, we can calculate the node voltages. So how? So V1, you know, right? It is given as 220 volt here. So V1 is 220 at an angle 0 volts. So V2 will be V1 minus I12 Z12. Z12 is here, it is given. This is Z23, this is Z34. So just you need to put the value here. V1, I12 you have calculated here, and Z12 is given. So if you put the values and calculate, so similarly V3 will be V2 minus I23 Z23, and V4 will be finally V3 minus I34 Z34. So once you have calculated the values of this V2, V3, V4, after that you can finally calculate the substation kVA output, right? So S naught, so if I consider this as the 0th node as a substation node, so that will be V1, S is VI conjugate, so V1 I1 conjugate. So V1 you know, and I1 you have calculated already. I1 is nothing but here I12, right? So if you do that, you will get this somewhat around 21.93933 angle 142 degree kVA. So this is your final answer. So 21.9 means it is option C. So these two questions were remaining from the previous time. Now we will go to this week's discussion. So for this week, we will be discussing about the effect of capacitors in distribution system. Right. So first here we will see the basic notation or sign convention for reactive power. So if we have a node where we have a generator connected, and this is the generator injected power Pg plus J Qg. So here, if the Q generated is positive, that means it is injecting the reactive power into the bus at lagging power factor, and this is injection. When it is 0, that means it is not injecting any reactive power, which means only active power is injecting, which is your unity power factor mode. And if Qg is negative, means this is leading VAR or leading generation of reactive power, and that means here the generator will absorb the reactive power. For load, we have a slightly different notation. So if you have a node where a load is connected, and let's say it is drawing PD plus J QD amount of power, then here whenever QD is positive, QD greater than 0, then here also lagging load, but it is drawing the reactive power. Here when Q was positive, it was injecting the reactive power generator. For QD equal to 0 means the load is perfectly resistive, we can say, or it is your unity power factor mode. That means it is only taking active power. And whenever QD is less than 0, so this is a leading load, and instead of consuming Q, the load is here injecting the reactive power. So this is the basic sign convention that we use for reactive power. And let's say if a node has both generation and load, then the net, or we can say equivalent expression for the active and reactive power, can be written as PD minus PG plus J times Q demand or Q load minus QG. So these are the expressions. Now for these capacitors, so we can connect them either in series, so either series connected capacitors or shunt. So depending upon whether the capacitor is connected in series or shunt, they provide with different advantages. So we will just see in brief what are those first, and then we'll go in detail. So for whenever we have a series capacitor, its main aim is to increase, or we can rather say improve, not increase, to improve the voltage of the system. So to improve the voltage means either it means rise in or decrease in voltage drop, we can say decrease in voltage drop, which will lead to your better voltage regulation. How it is done, we'll see it afterwards. And due to this voltage improvement in the system, the byproduct, you can say, due to improved voltages, that there is decrease in system losses also. How we will see the expressions? So the main motive to connect a series capacitor is for the voltage improvement. That's why it is sometimes called as a voltage regulator. Similarly, for shunt capacitor, the main aim to connect a capacitor in shunt to the system is to decrease the losses of the system. is the system losses. And this is your main motor. And as a substitute or as a byproduct, due to the decreased losses, there will be improvement in voltage profile. So its function is similar to your synchronous condenser. And another important point is that this capacitor, so the effect of whether this shunt or series capacitor, it is local. The effect of that is, what do you mean by local? It is a local phenomenon that let's say I have a distribution system like this with different radial paths also, let's say like this. So, and let's say I have a capacitor which is connected here at the, sorry. So let's say I have a capacitor connected at the end. So this is the shunt capacitor, right? Because it is here connected. So the effect of this capacitor will be more pronounced in this location. So at these branches, you can see the effect of shunt capacitor more. So in this head part section, in this part, so in this part also you will see some effect, but it will be lower. The major effect you can see at the neighboring nodes where it is connected. So that's why we call that the effect of capacitor. It is a local phenomenon. So due to this only we get the, so we'll discuss it in the last. For this only we require to choose a suitable location where to install the capacitor so that you can get the maximum benefit. So that analysis you need to be done, and for that we study the optimal placement of capacitor in a distribution system. So before installing the capacitor, we do the analysis. So at in layman terms, I can say that we'll connect the capacitor at each node, and we will see how much. Let's say this you want to study for shunt capacitor. If you connect at this end, there will be certain decrease in the system losses. If I connect it somewhere in the middle, there will be different system losses. And when I connected here at the substation side, then there will be some other values of losses. So at which position of the capacitor I get the lowest losses, that is the best performance, so I will install my capacitor at that location only. So for that, that we don't do like this, as I explained. So for that we write the code, and it will tell us what is the best suited node or best suitable location for installing the capacitor to get the lowest system losses or voltage, whatever you want. So if you see the capacitor, so first we have a single capacitor, right? So a element, capacitive element that we say, which is simply one capacitor. Then we have a capacitor unit. So after that, you get a capacitor segment. So in a capacitor unit, you can have multiple capacitor elements connected in different fashion, right? So it is combination of capacitive elements. Similarly, for a segment, so it is a unit of capacitive unit along with its control and protection. So with the capacitive unit, if you have its control and protection unit also, then we call it as a segment. After that, we have a capacitive module. So this segment is basically a single phase type. So when you group the segment, capacitive segment basically, to get a three-phase arrangement, so that will be called as a capacitive module. And similarly, lastly, we have a assembly, which is called a capacitive bank. So it is a assembly of capacitive modules, which are connected electrically. So this is the different structure or types of capacitor that we have. So next is how we decide that how much amount of capacitive compensation we require. So next question that arises is what should be the rating basically? Because once you know the location, as I explained here, after that the question comes, what is the rating of this? What is the rating of capacitive bank? How to decide that? So as you know, the load on the system is not constant throughout the day, right? So it follows a certain pattern, which is the load curve that we say. So for the load curve here, let's say it is demand versus time. So let's say it follows a pattern like this, right? So if you see here, the load initially it is at this point, then it is increasing to here. After that, there is a dip in the load, and again it is increasing to a certain value. So how to decide that what amount of capacitive compensation we need for different values of load? So for that, what we will do, we will divide this load curve into different segments, you can say. How? So the lowest load on the system is here, right? And let's say next is here, and the next segment is here. So first, what you need to do, let's say this is PD1, PD2, PD3. So first I will fix, for the calculation, I will fix the load demand at PD1 and calculate the rating of capacitor required. So let's say that gives the value as QC1. So if you can see that this much amount of load is always, this PD1 amount of load is always present in the system. The load is always either PD1 or greater than this. So what you need that whenever the load is PD1 means you require QC1 of the compensation. So throughout the day, you need that this QC1 should be switched on. So I fix at the step number 1, I install QC1 amount of var rating of capacitor which will be switched on throughout the day. Why throughout the day? Because my load will be always greater than or equal to this PD1 throughout the day. So for that, QC1 also should has to be switched on throughout the day. After that, depending upon the loading of the system, I need to switch on or off other capacitors. So after that, what I will do, I will fix the load at PD2 and calculate the rating of capacitor required. So let's say that gives me some QC2 value. Now what you need to do, you need to have a capacitor bank which has let's say some different combination of capacitors. So let's say when you switch is in one position, you get 5 MVAR. When it is in second position, it is giving 10 MVAR. In the third position, it is giving 15 MVAR and so on. So different combinations you can make to get the reactive power from the bank. So let's say this QC1 was 5. So what you will do, you will switch on this 5 MVAR module throughout the day. And whenever the load is between, so this is whenever load is between PD2 and PD1, you will switch on such that the Q net will be QC2. So I am saying Q net means earlier QC1 is always on, means QC1 plus certain Q additional you need to add such that QC2 amount of reactive power is derived. Similarly, whenever the load is between PD3 to PD2, I will switch on such that the net reactive power is now equal to QC3. So QC1 is always on. So QC1 plus Q certain additional should be equal to QC3. And this certain additional reactive power you can get through this combination of capacitor bank that you have. So this way the voltage of the system is managed in the distribution system throughout the day. So mostly what they will do whenever there is load is high on the system. So whenever there is load is more, that means you can say the drop will be more because more current are there, losses will be more. So for that, what you need to do, you need to switch on the capacitor, switch on additional capacitor to improve the voltage. And whenever the load is decreasing, so at that time you can switch off the capacitor, or sometimes it may so happen that you need to also switch on reactor to decrease the voltage, because it may so happen that the load is so low that the voltage at the distribution system is very high. So in order to decrease the voltage of the system, not only you need to switch off the capacitor, but also you need to switch on the reactors which will absorb the extra reactive power to decrease the voltage. So is this clear, or some confusion is there? You can ask, I can clarify. because actually I'm telling something very fast or something, so whether it is clear to you. Okay, I think we will proceed then. So we'll see the phasor diagram for both this series and shunt setting. Okay, so first let us see when a capacitor is connected in series, what happens. So first is series connection, series capacitor. Right, so series means, so this is your sending end, then you have the line parameters R and X, and here I have a capacitor connected in series. So that my voltage at the receiving end is VR, and let's say the current flowing here is I, and this is, let's say, XC. So if I draw the phasor diagram, so I'll start from VR, and let's say it is a lagging current I at an angle theta. So now from VR I need to have IR. So R is having no phase, means IR will be parallel to this I phasor, right? But its magnitude will be less because R will be less than 1. And now I need to have the component I times XL. So that will be, XL will rotate this phasor by 90 degrees, right? Because you have that J operator, so that will rotate it by 90 degrees. So hence you will get something like this. So this will be 90 degrees. So you get I times XL. Now this XC is basically its direction will be opposite to XL, because if this is positive then this will be negative. So if I let's say I times XC is this, or let me just write it clearly. So this is your I times XL, this phasor, and this phasor is, magnitude is I times XC, and what about the remaining, that will be from here to here, that will be I times XL minus XC, and then from this point here, if I join, I will get my sending end voltage at an angle delta from VR, right? So let us say this is Vs dash and this is Vs dash, and let's say this is delta dash. So if you remember in the previous class we also did this same phasor diagram but without the capacitor. So here, there we had seen these components. So we had seen that this angle was theta also. Yes. So this So this is also theta, and finally we had seen that this was I times xl minus xc sine theta, and this is just your I r cos theta. Same way only, just that this vector length earlier it was I xl sine theta, but now since there is a capacitor, it is xl minus xc. So from here I can write that Vs dash cos delta dash, which is nothing but this one, right? So this to this here, Vs dash cos delta dash, and here to here it is Vr. So I can write it as Vr plus IR cos theta plus I XL minus XC sin theta. And if we know this delta is small, if delta is near about 0, then cos delta is near to 1. So we can directly write that Vs dash is Vr plus this IR cos theta plus I XL sin theta minus I XC sin theta. So this was, if you remember, this part was in the previous expression, right, without the capacitor. So Vs dash with capacitor is same as Vs without capacitor minus this Ixc sin theta. So you can say that the voltage, that rise that you get due to the capacitor is this term Ixc sin theta. So I can write the voltage rise due to series capacitor is Ixc sin theta, right? So what we saw, that when we connect a series capacitor, what it is doing, it is helping us to minimize the voltage drop due to the line inductive reactance. That means, what was the voltage drop due to line inductive reactance? That was IXL sin theta. So due to this series capacitor, we have, it is reducing by Ixc sin theta. This is minus part, right? This is due to the effect of series capacitor. So what will happen due to this voltage drop? There will be improved voltage regulation, or there is, you can say, normally it is on that boost in voltage or voltage boost in the system, and that is depending upon which quantity, this I, right? I Xc sin theta and the power factor, because Xc is fixed. Once you install the capacitor, means if frequency is fixed, F is 50, and C you have installed at certain quantity C, so Xc is also fixed. So what is varying here in this voltage rise expression Ixc sin theta? So it is depending upon, first is your current I magnitude, and is also depend on power factor of this current, the sin theta. Is, what was this theta? Is basically angle between your VR and I, right? Angle between. So what is the reduction in loss? How? Due to this voltage basically rise or voltage boost, you can see it will indirectly, this voltage boost will indirectly lead to decrease in system losses. How? If you remember the expression for power loss, it was R times P square plus Q square times voltage magnitude square. And similarly, Q loss was X times P square plus Q square times V square. So whenever there is voltage boost due to series capacitor, means this will rise, so loss will decrease. It is inversely related, right? So due to the voltage boost, there will be a decrease in system losses. So if I write the expression, so P loss with series capacitor SC by P loss without series capacitor. So that is inversely proportional, means here it will be V magnitude square without series capacitor divided by V square with series capacitor. So what will be this ratio? Will be it greater than 1 or less than 1? Can you say? This term here. So due to series capacitor, the voltage will rise, right? So that means that your voltage with series capacitor is greater than voltage without series capacitor. So that means this will be less than 1. So if this is less than 1, means your power loss with series capacitor will be this ratio, which is less than 1 times power loss without series capacitor. So from here I can say that power loss with series capacitor, what will be? It will be less than P loss without series capacitor. Okay, so another thing, just you can see that here the series capacitor, it is not affecting this current I. The current I is same and this theta is also fixed. When you have the series capacitor, it is not affecting these parameters I and theta. So we'll see. Before that, there was this concept of overcompensation. So what was there in overcompensation? It was nothing. It was just that whenever we have leading condition, right? Leading power factor means now your current will lead the voltage by some angle theta. So this is your I So this will be your parallel to this IR, and 90 degree to this will be IXL. Then I will subtract this IXC. So this will be the final position here. So this will be IXL minus XC. And finally, then I'll get the VS dash at an angle delta dash. So here what will happen? Your VS dash is decreasing, right? So if we take the extreme case for unity power factor, so that your cos theta is 1, then sin theta is 0, then what will be your voltage drop? That will be IR cos theta minus I XC minus XL sin theta. So this is for the applications where your resistance is greater than the inductive reactance. And here XC is greater than XL. XC is greater than XL, so that this is positive. So if I substitute this here, then I'll get voltage dropped as IR. And since R, I have said that this is greater, so voltage drop is very high. This was overcompensation. And now another last one was a shunt capacitor. So whenever we have a shunt capacitor, so this is your line with parameters R and XL, and now you have a capacitor connected here. So let this be Vs dash, this be I dash, this be IC, this be I, and the voltage here be VR. So you can see here I dash equal to I plus IC. So if I draw the phasor diagram here, it will be something like first VR, then let's say initially the angle I with angle theta. Now what will happen along with I, if I add IC, then I will get I dash, right? So if I add IC here, so IC will be just J, right? So it is 90 degree here to VR, that is IC. and the resultant of these two you will get as I dash. I dash at an angle, we can say new angle theta dash. Right. So what will be the drop? It will be VR I dash times R, then I dash times XL. So that will give us VS dash at an angle delta dash. So due to shunt capacitor, here there is change in I magnitude and change in power factor, right? I dash and theta dash, you can see here. So what this shunt capacitor is doing, it is basically, we can say, it is drawing the leading current to cancel the lagging component of inductive load. So here you can see theta is changing to theta dash. So theta dash is decreasing, right? So theta is greater than theta dash. So power factor cos theta dash will be greater than cos theta, right? So we can say there is improvement in power factor, and also the current I dash is decreased, and as a byproduct this is leading to your drop in voltage. So we can say voltage is improved. But mostly our aim for shunt capacitor is for losses, right? And finally, there was this economic justification for shunt capacitors. So first point was released generation capacity. So if you remember, I talked about this capability curve in the previous week also. So there we had seen that is my screen visible now? Okay, anyways. Yeah, so we talked about this capability curve, right? So let's say the generator rating is S. So this S is fixed. So what is happening when you are connecting the shunt capacitor? What you are doing is you are locally solving this Q, right? At the load end only the Q is being supplied by the capacitor. So that means the Q generated by the generator, this Qg will decrease because it is being fulfilled by the capacitor. And whenever this Qg will decrease, so you can see here Qg will decrease means, and Sg is fixed, so Pg will increase. So that's why it is saying that there is release in generation capacity. So what we do generally is we supply the reactive power locally with the help of this capacitor or FACTS devices, so that the generator can supply more active power. See here. So if you want to operate at this point where Pg is maximum, active power is maximum, but here to generate maximum active power, the reactive power generated is zero. So this is only possible only when the reactive demand is supplied by the capacitor locally at the load end. So for that it is said that released generation capacity. Next is also released transmission capacity. So after this generation, what happens? This power is flowing through your transmission lines, right? And these transmission lines, they have certain limit. So current certain limits on their current carrying capacity. This current, it is having two components, right? Real and imaginary. So the real is for the active part and imaginary is for the reactive power part. So both similarly here also PL square plus QL square is the, let's say the thermal limit of this line is SL square. So this is also fixed. So in order to, we can say, transmit more amount of active power, we need that the reactive power transmitted is minimum. So whenever you install these capacitors, your Q transmitted in the transmission line is decreased. So whenever Q transmitted is decreased means for same transmission line with limit SL, you can supply more active power, or you can basically transmit or send. You can transmit, transport. You can transport more active power, and that is what we want because the useful part is only the active part. So whenever we are connecting capacitors, so likewise there is released transmission capacity also. The next is for the distribution system. Released substation capacity. So why substation capacity? So this is your transformer, and here is a substation, and from here this is the grid, this is the substation. So the substation will draw, and let's say here it is a distribution system with certain load, let's say PD and QD. So what will happen that when you connect this, what will be this rating of this or current drawn by the substation? Similarly, there will be real and imaginary part for this current drawn from grid. So with the capacitor, this reactive part or imaginary of current magnitude will decrease. So this will decrease means what is the capacity of the substation transformer? That is nothing but your V into I conjugate, right? So whenever there is a decrease in I means there is decrease in kV rating of this transformer also. Yeah. So what I was saying that there will be decrease in kVA rating of the substation transformer. And additionally, we had seen other also advantages such as decrease in loss, decrease in voltage drop, increase in voltage regulation. Then similar to the transmission capacity, there is also release in capacity of feeder of distribution system. Then there will be improvement, saving due to system improvement or over expansion. So what do you mean by this is if your lines are overloaded, so the solution is what? To build new lines to supply this system. But what you can do, you can locally supply the reactive power so that with the same lines you can supply more active power for the more loads. So that is meant by saving due to improvement of overexpansion. And there will be also revenue increase due to voltage improvement. So this you can see whenever there is power factor improvement, it leads in decrease in the bill of the system of your house or the grid also. So whenever such thing happens, then the revenue is also saved. So after that, then I think let us see the questions. So the first question is which type of capacitor have similar effect as overexcited synchronous condension? Series, shunt, or both? What do you think is the correct answer? Yeah, it is shunt capacitor. Series capacitors, we saw that it has effect similar to your voltage regulator. The next question is that low fire factor, a series capacitor produces less voltage rise, more voltage rise, equal voltage rise. You are seeing less voltage rise. What was the main motive or main function or main intention to install series capacitor? Was it for voltage improvement or losses? Similarly for shunt capacitor. So we saw that shunt capacitor, we are doing it for decreasing the system losses, while for series capacitor, we are doing it for voltage improvement. And due to this, in the shunt capacitor, whenever there is this decrease in system losses, as a byproduct, we get certain improvement in voltage, little. Uh, so that will be less than this series capacitor. So that's why it series capacitor will produce more voltage rise than a shunt capacitor at your low power factor. Now similarly, a three-phase round rotor synchronous generator delivers this power zero point 0.6 plus G 0.6 to infinite bus, the voltage of which is fixed at 1 per unit. The total synchronous reactance of the machine and line is 0.85. Armature resistance is negligible. So it is proposed to add a series capacitor in connecting the line such that the maximum power transmitting capacity of the machine increases by 25% when field excitation is kept constant. Find the capacitive reactance of series capacitor to be connected to the line. So here, basically, if you remember the expression for power that can be basically transmitted here, that we write as EV by X sine delta, right? So when this will be maximum? When sine delta is 1, right? So that it is EV by X. So here the X is given for the machine as well as for the line. It is given as 0.85. Right. So what will be the, if I take P max 1 by P max 2, so that will be EV and E, these are constant, right? Only X is there, so it is inversely proportional, means you get X2 by X1. So from here it is saying that such that the increases by 25%. So P max 2 is 1.25 times P max 1, X2, and X1 is 0.85. So from here I get X2 as 0.85 divided by 1.25. And how much that will be? This is right, right? So this will be 0.68. Now you know that the equivalent reactance required is 0.68. So earlier it was 0.85. So what additionally you require? So x additional is x1 minus x2. So 0.85 minus 0.68. So that will be 0.17 per unit. And how this additional reactance will be added with the help of this capacitor. So what will be this? You know this, right? Infinite single machine invariant bus we saw. This is your X, this is your EV. So 0.17, so option C. Okay. The next question says star connected 440 volt 50 hertz induction motor. So line current is given 20 ampere and power factor is given. Three ideal capacitors in star fashion are used to raise the power factor to 0.95. So find the rating of this capacitor bank in kVA. So it is asked in kVA, but you know that the capacitor, it cannot generate or consume any active power. So P capacitor is 0 basically. So the rating in kVA is same as your its reactive power rating. So let us first here calculate the demand. So that will be root 3 VLI cos theta. So root 3 440, IL is 20 and it is 0.85, right? So this you will get as 12.956 kilowatt. And what will be the reactive? That will be same root 3 VLIL sin theta. So sine of cos inverse of 0.85, and here it will get as 8.029 kVAR. So the first you can say that PD equal to PG plus PC, but we know this is 0. So the P generated or P source is 12.956 kilowatt. And what about Q generated? It will be PG tan phi, right? So PG is 12.956 tan of cos inverse of. So what is the power factor now? It is 0.95. So you will get as 4.258 kVAR. But we know that QD is QG plus Q capacitor. So from here you can get Q capacitor as QD minus QG. So it is 8.029 minus 4.258. So that you get as 3.778 kVAR. 8.029 minus 4.258. Yes. So the kVA rating of the capacitor is same as your QC because PC is 0, so it is 3.778 kVR. So it is B. Okay, now let's see the next one. So again, a star connected for 40 volt 50 hertz induction motor. Same is, so here only the capacitance, it is same question as previous, only here instead of kV rating, the capacitance capacitor rating is asked in farads. So we had calculated the three-phase power rating of the capacitor bank as 3.778 kVR. So now we'll do the per phase cancel calculations. So per phase rating of the capacitor is 3.778 by 3, which you'll get as 1.259 kVR. Now this will be same as V square by XC, right? V square by XC is 1.259 kVR. So XC is 1 by j omega c. 1 by omega is 2 pi f. C per phase 1.259 kVR. So C per phase will be 1. I can write it here. C per phase will be 1.259 into 10 to the power 3 divided by 100 pi into here B, since we are doing single phase means here B is again line to neutral. Earlier question we had done three phase, that's why it was line to line. So it is 440 by root 3 square. So from here you will get it as 1.25. So it is 3, 4, 5, 6, 62.1 microfarad. So that is your C. So next question is, similarly a load is supplied by a 440 volt 50 hertz source. The active and reactive power by the loads are such that range is given. So P is between 10 to 12.5 kilowatt and Q is between 6 to 7.5 kVR. So an overexcited synchronous condenser at no load is connected across the load and generates 5 kVR of reactive power. The maximum power factor that can be observed across the load after synchronous condenser is connected. So we had seen that this synchronous condenser is similar to your shunt capacitor, right? And that is given as 5 kVR. So if we have to calculate the maximum power factor, Then your PD should be Pmax should be Pmax. How much is Pmax? It is 12.5 kilowatt, and QD should be Qmin, and it should be 6 kVAr. That you can easily see from this power triangle, right? So we need cos theta is, so for this to be maximum, P has to maximum and Q has to be minimum, right? So that this denominator will be increased. So now whenever you connect a synchronous condenser, so you know PC will be 0, so that your PG is equal to your P demand, and QG plus QC is your Q demand. So this gives my QG as, your Q demand was 6, and this is generating 5. QC is 5, right? Minus 5, so 1 kVAr. So from here you can get maximum power factor as PG so here I can get it as 12.5 square plus 1 square. So that gives out 0.99681 lagging. So that is your option C. Now 4-bus distribution system. It is given here with line and load data are given, and the base MV and KV are given. So ideal compensating device is injecting constant leading power of 160 kVAr connected at bus 3. Then taking the initial guesses 1 angle 0 for all buses, calculate the load, and so here what you need to find, oh, you need to find the voltage magnitude at bus 3. Okay, so it is just your load flow, but here in addition to the load you have a shunt capacitor at node 3. So let us see how that will change the calculation. So let us first convert everything to per unit. So Z base is your kV square by MVA. So it will be 121. So similarly, then you can calculate the Z per unit as Z actual by Z base. So then you can convert these impedances here. this in per unit by dividing. Similarly, for the load, you need to divide by base MVA. So it is 1 MVA means 1000 kVA. So, so that will give you in per unit here also. So let us calculate the load first. So at node 2 it is just the load, right? So that will be 0.25 plus J 0.2. At node 3 that will be PL3 plus J QL3 minus this QC3. So that will give us 0.185 plus J 0.005. These are in per unit. So this is the equivalent load at node 3. Similarly for 4, it is PL4 plus J QL4. So that is 0.09 plus J 0.075 per unit. From that, now let us calculate the injected currents at node. Let me insert a new slide. So the node current I2, basically, you know, right, S2 is V2 into I2 conjugate. So from here you can calculate I2 as S2 by V2 conjugate. So this will be then PL2 minus JQL2 for conjugate divided by V2 conjugate. So V2 we are taking 1 angle 0 as initial guess, so its conjugate will also be 1 angle 0. So this is same as PL2 minus JQL2. So this was 0.25 minus J 0.2. Similarly, I3 will be S3 by V3 conjugate. So that will just be PL3 minus JQL3. This is net, considering both the load and the capacitor. So this is 0.85. 0.005. I4 is S4 by V4. PL4 minus JQL4. that is 0.09 minus J 0.075. So once I know the node current, I can calculate the branch currents, right? So what will be I34? I34 is same as your I4. Let me write them in small. And I23 will be I3 plus I4, and I12 will be I2 plus I3 plus I4. Now we have calculated this current, that was your backward sweep. Now for forward sweep, we'll calculate the voltages. So V21 will be V1 minus I12 Z12. So I12 in the first iteration, this in the 0th iteration. So if you substitute these values, you will get it as 0.9861 angle 0.099 degree per unit. Then V31 will be V21 minus I23 Z23. Right? V2 calculated, V3 calculated. So that will give as nearly 0.9774 at an angle 0.0815 degree per unit. Lastly, at the fourth node, it is V31 minus I34 Z34. So that will give me as 0.9764, which was V31 minus I34 Z34. This is 0.9764, 0.098 degree per unit. So that gives us 0.9764, option B. Okay, now I think same question, but here it is asked that using the current obtained in first iteration, find the power loss in the branch 3-4. So active power loss, we loss 3-4. So that will be I34 square R34. So that will be in per unit, and then we'll multiply the base value to get an actual. So 5000, right? This will be in kilowatt, and this will give us 0.098 113 kilowatt. So that is option D. Now for the ninth question, again, I think this is the same question. Here, reactive power loss of the system. So means everything you need to consider, both 1, 2, 2, 3, and 3, 4. So that will be same as when you calculate the injection at node 1. So let us calculate that. So I12 we have calculated at the end of first iteration. So that is PL2 minus JQL2 divided by V2 first iteration conjugate plus PL3 minus JQL3 V3 first iteration conjugate. Similarly, PL4 minus JQL4 V4 first iteration conjugate. So I will get it as just put the values here which we have calculated this, right? This using this, and then you'll get it as yeah. So yes, so this will get you as 0.53545 minus J 0.28387. So the total reactive power supplied by the substation, so that will be imaginary part of V1 I121 conjugate into 1000. So that will be somewhat around 283.87 kVR. Now what is the total reactive load of the system? So that is J times here 200 plus 165 minus 160 because there is capacitor plus 75. So this is around 280 kVR. So total reactive power supplied by the substation is Q demand plus Q load, so that your Q loss substation is Q demand plus Q loss. So your Q loss is Q substation minus QD. So 283.87 minus 280, it gives us 3.87 kVR. So I hope this is clear. Now for the last question, it is So thermal generating station, the ratio of excitation time constant to prime mover time constant is greater than 1, equal to 1, or less than 1. See, can you tell it why it is so? Because prime mover is the mechanical part of the generation generator, right? So mechanical part. So they are bulky, heavy, we can say, which means they have more inertia. More inertia means whenever, so they'll take a more time to respond, right? So that's why. So it is excitation is to prime mover. So since this is uh, basically prime mover time constant is greater than excitation time constant, so this ratio will be less than 1, right? So I hope this was clear. If you have any doubt, you can ask. If not, then I think we can close the session for today and we'll meet in the next class for the discussion. Okay, then thank you. Thank you, Shiv Kumar Mahato. So we'll meet in the next week.